Hey everybody, today we're going to talk about probability. Why? Because we're launching into a new section of statistics called hypothesis testing. And our hypothesis tests, these scientific tests that let us know whether or not there's a difference between different groups, these scientific analyses require probability. Okay, so that's why we're taking a look at this. All right. And so we're looking at notebook 10, which is called probability. And we're going to start off with some basic rules of probability, and these are basically review for most people. And we're going to discuss theoretical versus empirical probability. So theoretical probabilities are where you calculate the probability, like rolling a die, the probability of getting a 3. Well, there's 6 outcomes that are all equally likely, and getting a 3, that's one of the 6, so the probability is 1/6. That's a theoretical probability. And empirical probability is where you simulate a die and you roll it a couple thousand times and you see how many threes you get. And you use the results from the simulation as your empirical probability. All right. So we have a machine that can do these simulations pretty quickly. And so we'll learn about the new dot sample method. Now, before we jump into the notebook, let me tell you that we're going to use the dot sample method. It's a table method, and we're going to use it to create these dice rolling examples. And we'll calculate probabilities that way. And then the second set of examples, we're going to use the computer's stats.binom.pmf function. Now, we actually have imported scipy.stats. Okay, so just like we have numpy, which is the numeric Python stuff, we have scipy, which is the scientific stuff for Python. And it's just a package that has some statistical functions that we need. And we've imported the scipy.stats, and we have this alias called stats, which refers back to it. Okay, so we're going to be using those. And so when I do the stats, well, I'll jump back into this, but you can see that I've got some suggestions about how exactly stuff goes in there, what the different values mean. So let's jump into the notebook and see what we've got. So running the initialization code, making sure that's all good. And notice we're importing scipy.stats as stats. So stats is the alias that I just described, right? Okay. And so the first thing we're talking about are these probabilities, the properties of probabilities. And the first one is probabilities are between 0 and 1. And that's in decimals, right? It's between 0% and 100%, right? If we convert to whole number percentages. And that makes sense. And then the closer it is to 100%, the closer the probability is to 1, the more likely it is to occur. And if the probability is equal to 100% or equal to 1, then it's virtually guaranteed, right? If it's close to 0, it's virtually impossible. If it's exactly 0, then it's virtually impossible. And the smaller it is, the closer to 0, the less likely it is to occur. And then we talk about this not E. And this is like if the chance of rain is 30%, then the chance of not rain is 70%. Let's assume that the weather guy did get it right this time. If the probability of rain is in fact 30%, then the probability of it not raining should be 70%. And again, it's just 1 minus the probability of the event. Okay, so you can look at these, and they also describe what I just did about theoretical probability versus empirical probability. Take a look at that, but let's jump on down. Sorry. Can't get this to move. Okay. And this is what I told you. So we're going to create this die. And notice it has 6 faces, 1, 2, 3, 4, 5, and 6. And then die.sample 10. It's like it's rolling the die 10 times and recording the face that comes up. So you notice that we got a lot of 1s. There was a 6, there was a 3, there was a 5, and at last there was a 3. And this die.histogram shows that sample. Okay, sorry, I'm having trouble getting it centered here. Okay, and this is a little choppy because the bin widths are only 0.5, and so here we create new bins that are 1 unit wide. And when we use these in the histogram looks nicer. So wait, I got to move up here and create the bins as an array and then put in the bins. And we see that the distribution of these probabilities, it's exactly flat. It's flat right across the top. Why? Because this is a uniform distribution. Every outcome is equally likely, so the histogram of the probabilities is flat. Every single outcome is equally likely. Okay? So we do another sample and histogram of what happens with the roll bins, and we notice there's some weird stuff here. Okay, so then we do 1,000 sample, a sample of size 1,000, and notice that the probabilities aren't perfectly flat, but they're getting a lot flatter, right? So as we go up to 1,000 trials in our sample, right, a sample size 1,000, we get the results look much more like the original distribution. Okay, and if we, oh, clear, let me get rid of the ink. Sorry, I was just trying to get rid of the ink. All right. And notice what we did here. This is 10,000 or 100,000? That's 100,000 trials. Okay. And notice how flat that is. So what are we illustrating here? Well, we're illustrating that we can use this dot sample. It's a table method to roll the die 100,000 times, and we can use dot hist, which we've used before, to create a histogram. And the result of 100,000 trials, the empirical probability almost is identical to the theoretical probability. Okay, we're getting the idea that, oh, if I run enough trials through my simulation, my empirical probability is going to match very, very closely to the theoretical probability. Okay? So here we're going to consider a situation where we flip 10 fair coins and count the heads. And the first question is, what's the probability that we get exactly 5 heads? And again, jumping back to the PowerPoint, let me just show you what's going on here. Right? So there's 3 things that I enter. The first thing that goes in is the number of correct. So we want 5 out of 12. The number of trials, that's 12. And the probability of success on each trial. Well, if it's, oops, sorry. If it's a coin flip, then of course that's 50-50. So let's jump back in here and see what we have. So what's the probability that we flip? Oh, I'm sorry, it's not 12, it's 10. 10 fair coins, flip them. What's the probability of getting exactly 5 heads? And look, here we go. The stats.binom.pmf, 5 successes out of 10 trials at a 50% chance of success. And you can see the probability of getting 5 correct out of 10 is about 24.5%. And the answer to the second question, what is the probability that we get 5 heads or less? Okay, so what does this NPA range of 6 do? Well, remember, it always starts counting at 0 if I don't specify. All right, so out of 10 trials, this is going to do 0, 1, 2, 3, 4, 5. So all of those number of successes. Okay, and it's going to add them all up. Why? Because on the outside of this, we're doing sum. So it's going to calculate all 6 of those, right? Number of successes 0, 1, 2, 3, 4, and 5. It's going to calculate all of those and add up the probabilities. Oh, and that kind of makes sense. There's a slightly more than 62% chance that if I flip a coin if I flip a fair coin 10 times, I'll get 5 or fewer heads. Okay, that makes sense. What's the probability we get at least 1 head? Okay, well notice here the MPA range. I don't want it to start at 0. And remember, the MPA range always starts counting one less than the stopping criteria. So this is gonna do the integers 1 through 10. Okay, and then again we have the sum function. It's gonna do all 10 of those and add them up. And believe it or not, we have almost 100%, right? We have 99.9% chance of getting at least one head, it makes sense, right? What's what if we don't get at least one head? Well, that means we got all tails, 10 out of 10 tails, which seems pretty surprising if it's a fair coin, right? So that probability does in fact make sense. And then what's the probability that we get at least one head? They're doing it another way, and notice that we get essentially the same thing. Here they're subtracting from 100%, and they're saying what's the probability of getting 0 successes? Okay, and again, it's essentially the same thing, a little less decimal place accuracy, but exactly the rain versus the chance of rain versus the chance of not rain, illustrating that. And then the graph of the distribution, okay, and don't worry about the baby error there. So you can see exactly what you'd think, that the histogram, the probabilities of these things happening, the biggest probability is sitting right there on 5 heads out of 10. And of course that makes sense. If it is a fair coin, in fact, you'd expect about 5 of the coin flips to be heads and about 5 to be tails. Now, that can vary a little bit. Sometimes you'll have 4 heads, sometimes you'll have 6 heads out of 10, and then 3 and 7 are a lot less likely. And then as we get further over to the weird distributions, like two heads and 8 tails, or 1 heads and 9 tails, those are clearly much less likely. Okay. And we do the same thing with a fair die that's rolled 20 times and count the number of fives. And again, we're always number of successes, number of trials, probability of success. And so the probability of getting exactly 12 fives is 1.3458 times 10 to the negative fifth. That's essentially 0. But that makes sense because there are a lot of different things that can happen. And we're asking what's the probability of getting 12 fives out of 20 dice rolls? And it's not that good. Here we're doing a sum. Why? Because we're doing 12 or more. So the MPA range is going from 12 to 20, right? The MPA range will stop counting one item before the stopping criteria. And you can see that one. And you can go through these. These are exactly the same as above. And I want to get to this famous example we have for the lady tasting tea. All right, so let's jump back. And so Ronald Fisher is the godfather of statistics, modern statistics. So he and Muriel Bristol worked at a research station. They're British, and so this is World War I era. I believe it's right after World War One. Um, and and so they're scientists that work at this research station, and they're working on the same project. So Dr. Bristol drops by Ron Fisher's office, and they're talking about their science project they're working on, and and so Fisher offers her some tea, and he's pouring a cup of tea, pours the tea in, and asks her if she wants some, and she declines it, and she says that he's already poured the tea in, but the tea will taste better if the milk was added first. So so Fisher's never heard of this. He pours his tea, and then if he wants some milk, he puts a little milk in it. And by the way, there is some science behind this if you think about it. If there's hot tea, if the tea was just boiling, so let's say the tea liquid is about 200 degrees, but the milk or the cream has been in the refrigerator, so it's what, 50 degrees? So you pour a couple tablespoons of milk into the tea, you have 50-degree liquid hitting 200-degree liquid, and it heats up really fast. And that really quick heating of the milk actually curdles it just slightly. And if you have discriminating taste buds, like apparently Dr. Bristol did, then you'll taste a slight difference. Okay? But if you put the 2 tablespoons of milk in the bottom of the cup and then pour the 200-degree tea in on top, that 50-degree milk will heat up much more slowly and it won't curdle. So apparently there's a small difference in taste based on whether you add the milk first or the tea first. Fisher never heard of this, so he proposes a blind taste test. And so they're going to give Dr. Bristol 8 cups of tea, and there are 4 where the tea was added first and 4 where the milk was added first. And she's supposed to separate them into 2 piles and milk first and tea first. And he says, okay, if you identify 7 or more correctly, we'll say that your claim that you can taste the difference has been established beyond question. And why is this important? Well, this is how Fisher came up with the idea of a hypothesis test. And we have a null hypothesis. It's a claim that cannot be established but only disproven using probability. Okay, so his null hypothesis is she can't really taste the difference. She's guessing. So it's like flipping a coin, right? So what's the probability of getting 8 coin flips correct out of 8? Okay, and so he's going to use that probability experiment as the baseline, and he's going to collect some data, and he's going to see how many out of 8 she can get correct. So let's jump back into the notebook. And again, what is the probability? So by the way, history records that she correctly identified all 8. So it turns out he was going to say that even 7 out of the 8 was fine, but let's look at why. So when we use the stats.binom PMF, 8 successes out of 8 trials, if she's guessing, that would have less than a 1% chance of happening. That would have about a 0.4 chance of happening. And then notice that here, so X is the probability that she gets 8 out of 8, Y is the probability that she gets 7 out of 8, Z is the probability that she gets 6 out of 8. And so we can see a couple of these others. Let me open up a cell. You don't have to do this, right? But X is the first one. We've already seen this. So let's look at Y. If she gets 7 out of 8 correct, wait, why is this? Okay. See, that's got a 3% chance of happening. Okay, and what's the probability that she gets 6 out of 8? Exactly 6 out of 8. Well, that has a 10 or 11% chance of happening. Okay, so why did Ron Fisher say 7 or 8 correct would be evidence? Well, because both of those were less than 5%. And he basically said, we're going to use this 0.05 cutoff. And it seemed good to him. And it turns out that, 100 years later, we're still using 0.05 as our baseline level of alpha. Okay. However, if she only got 6 correct, he was going to say, no, that's not evidence that she's not guessing at random. Okay. And then that led to the normal distribution. So we need to figure out these probabilities, and often we need to do it quickly. So we use the normal distribution, and the baseline normal distribution is called the standard normal, where the average equals 0 and the standard deviation equals 1. And by the way, for a normal distribution, this is the notation that we use. We use a capital N, that means normal. The first number is the mean, and then there's a comma, and then the second number is the standard deviation. So there we go. We can say really quickly, oh, hey, here's how we refer to a normal distribution. And this is the standard normal, so it's N 0, 1. And getting rid of the ink. Okay, so we can graph it. And this is the standard normal. Notice that it is centered at 0, and it has a standard deviation of 1. Okay, this is a standard normal like might be used for the SAT, where the average is 500 and the standard deviation is 100. Okay, and then it says suppose a test. Okay, the SAT does in fact have scores like this, that the average, so like there's an 800, so your SAT math score is out of 800 and your SAT verbal score is out of 800. So these sections They have an average of 500 and a standard deviation of 100. So what percentage of students score below 400? Well, notice that we're using the where x is less than 400, color it red, and there you go. And I'm sorry, let me move this up where you can see it. Okay. And we can calculate that. And about 15.8 or about 16% of students score 500 or lower. I'm sorry, 400 or lower. This red portion here. Okay. What's the probability that a randomly selected test will have a score below 400? Well, it's the exact same thing. Sorry. It's the exact same question. Okay, so what's the probability a randomly selected test will have a score between 400 and 700? Well, we're going to do the same thing, but we're going to shade, we're going to shade between 400 and 700, and then we can use stats.norm CDF to figure this out. And you can see the probability is about 82%, 81 to 82%. That if you take the math SAT, your math SAT score is between a 400 and a 700. And the area under the curve that's shaded is the percentage of the area that we get here, is this value, this probability percentage here. Okay, so standard units, what are those? So standard units are called z-scores. Why? Well, it tells us the number of standard deviations above or below average we are. So let's talk about what these values mean. So z equals x. So that's whatever score we're talking about. Okay, mu is the population mean, and sigma is the population standard deviation. And by the way, if we don't know mu and sigma because we don't know the population statistics, we can always use the sample statistics where x bar is the mean and s sub x is the standard deviation. Okay, but the z-score is x minus mu over sigma, is the score I'm evaluating minus the mean, and that difference divided by the standard deviation. All right. So why do we care? Well, for example, suppose we have fraternal twins, and one's a biological male, one's biological female, and the male is 6'5" and the female is 6'1". So assuming that the male distribution for biological males, the distribution of heights, is a normal distribution with an average of 69 inches and a standard deviation of 3, and the distribution of heights for females is a normal distribution with an average of 64 inches and a standard deviation of 4. And then who is the tallest compared to their biological sex, compared to their distribution? Okay, so we can find their z-scores, and you see the calculations right here. And this is for Rachel, right? So she is 73 inches tall. 6'1" is 73. She's 73 minus 64. Why? Because 64 is the mean in her distribution. The difference divided by 4. Why? Because the female sex has a standard deviation of 4 inches. Okay, and the same exact calculation for Richard. He's 77 inches tall minus the 69 inches average for his sex. And the difference is divided by 3. Okay, getting rid of the ink. And scooting down just a little bit so we actually do these. Sorry. And it turns out that in standard units, Richard is 2.2 and 2/3 standard deviations above average for males. Okay, that's good. And Rachel is 2 1/4 standard deviations above average. So they're both well above average. But Richard is further above average compared to the biological males than Rachel is compared to the biological females. So this is what we mean by standard units. We can use these z-scores to compare scores in different distributions to each other to see whose is the most unusual. And then they do some show and tell and they give us, hey, here's a plot that shows Richard compared to his distribution. That's why the tiny little sliver of red, because he's very tall. There just aren't that many people taller than him. And then finally, they're showing what's called the empirical rule. Within one standard deviation of the mean, we find 68% of the scores in a normal distribution. And within two standard deviations, we find 95% of the population. And within three standard deviations, we find almost all of the population, right? 99.7% of the population. Now, the empirical rule is listed right here, right? One standard deviation captures 68%, and two standard deviations captures 95%, and three standard deviations captures 99.7. Now, they use this before calculators to help them roughly estimate these probabilities because they didn't have calculators, right? Now that we have calculators, we don't need the empirical rule quite as much, but this just covers the use of probability in statistics, right? And because of R.A. Fisher, who did the experiment with the lady tasting tea, that's why we use this alpha of 0.05. It's called the level of significance, right? And it's denoted with the Greek letter alpha. And then all of these hypothesis tests are going to result in a p-value. Okay, and we compare p to alpha. And if p is less than alpha, we say the result is significant. And what we'll be doing is we'll be rejecting the null hypothesis. And just to finish up, let's put the null and alternative hypothesis in terms of the lady tasting tea. So you can see that. Right, so the null hypothesis is that Dr. Muriel Bristol was going to guess with 50% accuracy. It was just a coin flip. She couldn't really taste the difference. The null hypothesis is she's just guessing. The alternative hypothesis is no. She's guessing it better than 50-50. She's got some knowledge. She's able to taste the difference, right? So in words, the null hypothesis is that Dr. Bristol was guessing, and the alternative hypothesis is no. Dr. Bristol, sorry, I put Brist. I left off the OL. Sorry about that. Dr. Bristol could taste the difference. Okay. So that's what we mean by hypothesis testing. We're going to have a null hypothesis that we can test with a probability simulation. So these hypothesis tests are going to spit out a p-value, which is the result of the probability simulation, the probability that the null is true. That's what the p-value is. And mark that down because this is important. Make a note. The p-value from a hypothesis test is the probability that the null hypothesis is true. And when p is small, we reject the null in favor of the alternative. All right, see you next time.